Welcome to another podcast. In this episode, we're going to be taking a look at a variation of parameters example involving a mixing problem. And so I have a compartmental system here, so we're going to analyze what's happening to the salt content in both tank 1 and tank 2 simultaneously as this system sort of flows through. And I've left a couple of pieces of information off because I want us to fill them in together. I want to consider first what's going on with tank X. It's losing at a rate of 3 liters per hour whatever solution's in X, but it's gaining at a rate of 2 liters per hour whatever's coming from Y. The net here is it's losing 3 but only gaining 2, which means that the flow rate here has to be 1 because I want to keep the tank have a consistent volume. So that's sort of an assumption here, is that both tanks are going to stay at a consistent volume. Similarly, if I look here at Y is gaining 3 and 4, but it's only losing 2, which means the flow rate here has to be 2 liters per hour as well. Now, if I don't introduce any salt into the system, then this is a homogeneous problem. And so whatever salt initially is in the system eventually is going to all go away, and the solution is going to be there's no salt in the system. But I'm going to introduce a little bit of salt via the fact that coming in to X from the outside here is salt with a concentration that decays over time. So I'm going to give that starting concentration as 5e to the negative t, and this would be in terms of gallons here. Or no, excuse me, in terms of I guess it would be grams of salt. I guess it doesn't really matter what the units are here, but this is the concentration that's entering. So you're looking at how X, which I guess pounds is the most appropriate thing here. So we could be looking at pounds of salt. Then what you're doing is you're looking at how many pounds per liter. And so if it's 5e to the negative t pounds times 1 liter per hour, then that gives you an idea of the concentration that's entering the system. And so if you recall sort of how to do this from earlier in the semester, I'm just going to consider what happens to X. The rate of change of X it depends on, well, it's losing 3X. So whatever the concentration is for X, it's losing it at a rate of 3 per hour, 3 liters per hour. But it's gaining 2 from Y. And then it's also gaining from the outside 1 liter per hour times that number of pounds. So it's gaining this many pounds of salt per hour. Because it's 5e to the negative t pounds per liter times 1 liter per hour, so it's going to be that many pounds per hour. So this is how it's changing. It's gaining, even though this is decaying, it's gaining salt content from the outside. And then this describes the interaction between the two tanks. Similarly, the change in the salt content for tank 2 for Y is it's going to be gaining 3 from X coming in through here. It's also gaining 1 through the outside, but what I didn't tell you is that this is going to be pure water coming in from the outside. So we're not gaining anything from the outside, so this is going to be plus 0. And then it's also losing 2 here and 2 here, so it's losing a total of 4 liters per hour from whatever the mixture is for Y. And so the system that we're looking at here is the following system. And it's inhomogeneous because I'm getting salt from the outside that's driving the system. So this is the outside forcing term. It describes how tank 1 is being forced and how tank 2 is being forced. And so this is the inhomogeneous system for this particular problem. And I just want to go ahead and find the general solution. So I want to find the general solution for the mixture involving X and Y as the solution. Okay, this T stands for transpose, which just means take the rows or take columns, turn them into rows, or vice versa. So this is the same thing as me saying the component xy. So those mean the same thing. So I want to find the state of salt content as a function of t for both x and y separately, even though we're solving it simultaneously. Well, the way to do that is to construct a fundamental matrix. So if my matrix A is -3, 2, 3, and -4, then my characteristic polynomial is lambda squared minus the trace. So the trace here is -7, so it's +7. And the determinant here is -12 +12 minus 6, so it's +6. So we've got lambda +1, lambda +6, which means that my eigenvalues are -1 and -6. Okay, if I actually let me change those, because in my notes I have them lambda 1 is -6 and lambda 2 is -1. It doesn't matter, but I just want to be consistent with the notes that I'm using. So what we have here then is calculating for lambda 1. So if lambda 1 is -6, then we have, I'm going to be adding 6 to each of these diagonals. So if I add 6 to -3, I get 3. If I add 6 to -4, I get 2. And so you can see here that the eigenvector that goes along with this, I've got to zero this out. So that eigenvector will have to be 2, -3. There's other ways to do it, but 2, -3 works. Similarly, for lambda 2, if lambda 2 is -1, then I'm adding 1 to the diagonal. So if I add 1 to -3, I get -2. Add 1 here, I get -3. Check to see that it's redundant. If I multiply this by -1, I get this column, so it is redundant. And so the vector here looks like 1, 1 is a good choice. So what this says then is that our solution is x of t equals c1 2 -3 e to the -6t plus c2 1, 1 e to the -t plus some inhomogeneous solution. And so the question is, how do you find the inhomogeneous solution? Well, it's equal to the fundamental matrix times the integral of the inverse of the fundamental matrix times the vector r dt. So what is the fundamental matrix for this problem? Well, it's simply the columns of the fundamental set. So the fundamental set of solutions is 2e to the -6t, -3e to the -6t, e to the -t, e to the -t. So that's our fundamental matrix. And I've got to find its inverse. So the inverse of this matrix, done in the normal way, remember let's just go ahead and do it all the steps. It's 1 over the determinant. So the determinant of this matrix is 2 plus 3, and notice that they're both e to the -7t's. So this is going to be 5 e to the -7t for the determinant, times the matrix where I switch the diagonals, and then I negate the off diagonals. So altogether, once this is calculated, you end up with 1/5 e to the 6t. So this is a constant. I'm going to multiply it by each piece. So 1/5 e to the 6t minus 1/5 e to the 6t, 3/5 e to the t, and 2/5 e to the t. So I'm just taking, this is the same thing as 1/5 e to the +7t. So I'm just taking that whole thing and I'm multiplying it by each piece. And so this is my inverse matrix. Okay, if I keep going with this, so I need to create a little bit more room for myself here. If I keep going with this, then the idea is I'll need to then update the pieces of my formula to find xp. So xp is the fundamental matrix. So I'm using this formula. It's the fundamental matrix integral the inverse matrix, which we just calculated, times the inhomogeneous vector r. Here's the vector r from the problem. It's the part that made it inhomogeneous. Like so. And so, looking at this, we'll take it sort of step by step here. We're going to do the integration step first. Or actually, we're going to do the multiplication step first. So multiply these two, well, vector and matrix. So if you multiply those two together, what you'll end up with here is, it looks like e to the 5t. So you get 5 times 1/5 is 1. E to the negative t times e to the 6t is e to the 5t. And then the 0 zeroes out this entire second column. So you're just taking this times the first column to give you the column here. So 5 times 3/5 is 3. E to the 0, which is just 3, dt. And so now I'm ready to do the integration step. And you integrate a vector or a matrix term-wise. So each component-wise is really the term. So integrate this component, e to the 5t is 1/5 e to the 5t. And the integral of 3 is 3t. So finally you multiply this column vector times this matrix. And so the first component would be, it would be 2/5. Well, the best way to do it, we'll do it all at once here. You're going to get 2/5 e to the negative t plus 3t e to the negative t. Then you're going to get negative 3/5 e to the negative t plus 3t e to the negative t. So what is our final answer? Well, our final answer is the salt content in tank X varies according to, I'm just going to read across the top component here, C1 times 2 e to the negative 6t plus C2 e to the negative t plus the top component of x of p, which is, the best way to write this is as 2/5 plus 3t e to the negative t. So that's the top component of x of p. Similarly, the solution for y of t is, I'm reading across the bottom component now, it's minus 3c1 e to the negative 6t plus c2 e to the negative t plus the bottom component here is minus 3/5 plus 3t e to the negative t. And so all combined, this explains what's happening in each of the tanks X and Y over time, where we used variation of parameters to come up with this part of each solution. Up till now, all we would have been able to come up with is the homogeneous solution, but using variation of parameters, we can now solve inhomogeneous systems as well. All right, thank you for watching.